Hello everyone. We'll try some of the problems for chapter 5 and 6. And here we are going to learn about many things, but basically it's dynamics or kinetics. That means we are trying to understand the force. So there will be many forces, like a gravitational force, and the normal force, and the tension. And of course, there is something else, which is the centripetal force for circular motion. So we are going to deal with something different from the previous chapters. So you need to understand we are in the realm of dynamics, and note that for even for the kinematics, it is a circular, so that is no longer a linear motion. It is circular motions. So we have to have a very different perspective. Okay, let's start with the circular motion. First of all, we are going to have a circular motion. The car passes over a rise in the roadway such that top of the rise here is shaped like a circle of the radius of this length. At the moment, the car is at the top of the rise. Its velocity is given by this one. And the constant acceleration parallel to the road is given by this way. What is the magnitude of a total acceleration vector for the car at this instant? So first of all, we need to understand what is not given and what is given. So here are the what are given. The radius of curvature on the top. So that means if you think about it, is circular motions. So radius is given. Base speed, a speed at that instant when the car reaches, then we have a velocity. And then we have a tangential acceleration is given as well, at. And then at the top of the circular rise, so normal acceleration points toward the circle center. So here is a two different type of accelerations. So at the center here, we may have a tangential acceleration as well as normal accelerations. And then this is the centripetal force. So if you have a certain radius and velocity, then acceleration is expressed in terms of a radius and the velocity. Okay. So tangential acceleration is along the roadway, at. So we have a at here and an. We need to know that. Total acceleration magnitude is going to given by these two components, at and an. And then you can find out the total acceleration magnitude is given by this one. And then what is given? The R and V is given so that we know an. At is already given in terms of number. So we all know that. Then we can find out the accelerations. here. So total acceleration is given by this one. And then you can do the numerical calculation by yourself. And then another circular motion, a bucket of water falls around a vertical circle over a radius of 7.93 centimeters. What is the minimum speed? Minimum speed that the bucket must have at the top of a circular motion if the water is not to spill out of the upside down bucket. Take the gravitational acceleration as a g. Okay. So let's try to think about, visualize. This process is also very important in the physics as well as any type of science. So the natural language is translated into diagram, the radius r, and then if it is swirling vertically, that means that there is a bucket and then there is a water. And then it is doing some kind of a velocity there. Okay. So this is the situation. And then they are trying to ask what is the B such that water is not spill out. Okay. At the top of a circle, for the water to just not spill, the normal force of the water at the top must be zero. So in other words, at here, we have two types of forces. So of course, the gravitational is here, gravity downward. And then there is also another force here, okay? And then you see that which is a centrifugal force or centripetal force, depending upon your viewpoint. But anyhow, there is a certain force that is pushing the water outside, and the water, the other force are pushing the water downward. So that this is the centrifugal. I'm sorry, it is centrifugal at the top, and it should match the gravitational pull. This is the condition. So we have a process, we have a natural language problem statement, and then we get this diagram. And from the diagram, we note that the interpretation of this natural language is now turned into these equations. Okay, and then from this, we get V square is GR. And then do we know all the parameters? Yes, we do. We know the G and we know the R. So we can find out the velocity. Okay. A bicycle initially at rest accelerates uniformly along a circular path at a flat horizontal surface. The bicycle makes 1/3 of the circle before it skis off. So that is another important natural language. If the coefficient of the static friction between the bicycle and the surface known and equals this number, find the tangential acceleration taking gravitational acceleration as this one. So what is going to concern is that we have to think about two things. So instead, a previous case, we have a gravitational force as well as the circular motion force, which is a centrifugal in this case. And similarly, what is going to happen here is that if you look at what is happening, so initially it was at rest, and then it is moving. So 1/3 is this much, right? So as the bicycle moves along the circular path, and then it skis up, skis up. So that's the very natural language, but we need to figure out what it means in physics. And there is another very important thing. So there is a coefficient of static friction is given here, and then gravitational force is here. And then accelerate tangentially at a constant at, so that it is at, okay? And travels 1/3 of the circle before skidding. Zeta is given by this one. So first thing is that we need to find out what is happening so that the speed after traveling 1/3 of the circle. So arc length is given by r zeta from here to here. Yes, is given by this one. And then from the this distance, displacement, then what we have to have is if it is a constant accelerations, then we should have this relationship such as v final square minus v initial square is given by 2a, let's say, s initial or s final minus s initial. Okay, that's the thing. So this is the what we uh, uh, found here above. And then we have assumed that initial velocity was 0, so that the final velocity at the incident is happening. V square is given by this one. Okay, so that it is given by this value. And then hence the centripetal acceleration at that instant is given by centripetal acceleration is given by this one. Okay, so that what we are trying to do is that we know that in order to find out accelerations, and that there should be some kind of a two type of accelerations. One is keeping the bicycle on the circular path, and the other one is keeping away from the circular path. The first thing is that we found out the centripetal that corresponds to the acceleration to keep it on a circular path. And then what about something? So we have to think about frictions. So one level ground, only horizontal force is static frictions, whose minimum is given by this one. And what is going to happen here is that note that at 1/3 at this position. So that's what is happening here. Okay. Then on the level ground, so if you just uh, expand it, then you have a bicycle. Let's say, assume that this is an object. And then it is moving on. So it does not move up and down. And then the only force that is will happen is on the horizontal plane. Okay, so that what is going to happen here is that uh, we have frictional force, and then if it is the mass is m, and then there is a normal force that is pushing the object on the ground, and this is mg. And then frictional force will depend on this normal force. And then frictional force is given by mu s n, which is mu s mg. And what we are going to do is that the maximum horizontal acceleration magnitude available is this one. And required horizontal acceleration vector combines perpendicular AT. Okay, so what is happening here is this one. So anything that is moving will be under the influence of two forces. One is the tangential as well as the, horizontal one. Okay, tangential and the horizontal one. And then what is going to happen here is that this one is given like this. And then what about AC? AC is given by this one, centripetal. Okay, so we are going to put the AC here, and then we have this one. And then what is going to happen here is that this total acceleration should match the frictional force. So to be clear, so that we have a AT and AC, okay? And then whatever the move was, there is always friction, okay? So that if one to have this kind of a acceleration this way, then there is a friction that is moving away from this track, okay? So that this frictional force should match that of the force that is keeping the track on the circular path. So that is these accelerations. And this acceleration has two components. One is the tangential and the other one is the centripetal, okay? And then we have just found out what the centripetal force is, and then it is given by this one. And this should match this force and keep it circle. And then this friction will kick out of the circle. And then this will be skied. So here is the natural language skied off. And then this is now the expression for skied off in our viewpoint. Okay. So there have been long way to reach this stage, but we have to note that there should be an expression in terms of physics to represent this natural language. Okay, once you get to this point, then it's relatively easy. Mathematics, AT is given by this one, and then just plug in the numbers, and then you can get the tangential accelerations. So key thing here is that try to apply the physical model that will fit to our natural language expression of the problem statement. Okay, now another problem, a block of a mass m equal to 1 kilogram is moving with a constant speed in a circle with the radius of this one on a frictionless table. This is another important things. And the block is attached to 1.5 kilogram mass. This is the capital M, and this is a small m. And through a hole in the table, find the speed with which m must move for m to stay at rest. Okay, so that when we say that something is at rest, that means there is some kind of equilibrium. Some of the force should be cancel out, but that's the thing we need to consider. So in this case, we have to consider there is a circular motion, and then note that this will have a certain force that will exert going outward. And then what is happening here is that means there is an inward tension along the string. And then once tension is given by single string, that means you have also tension. And then in this case, it is lifting up. Okay, so this is the important figure you need to keep working. So tension is always moving away from the object to the certain point. And same here is tension is moving away from the object to a certain point. So that we have but they are in the same magnitude. Note that in this case, we have a match in this central circular motion, but at the same time you have this uh, compensation of gravitation. So there is a two cases where we need to match the equilibrium in terms of this tension and circular motion and tension and gravitation. So let's try to find out what has been given. The mass small m is given, the radius is given, hanging mass capital M is given, G is known. Table is frictionless, and the code goes through the whole. So forces and conditions, the hanging mass capital M to stay at rest. So if you look at it, there's a T, and then there's a mg. So that it should be equilibrated. So that capital T is given by capital Mg. And we need to move our attention to small m, this small m mass. And then we note that if it is circular motion, we have this centrifugal force, and then it should be same as T, okay? And then we have a two equilibrium for the M, capital M, and small m, okay? And then from this, we can find out, we can equilibrate this one. And then we get these equations. And then after that, only after that, it's going to be very easy. So once we get to this point, V is given by this one. Capital M, small m, G, and R is already given, so that you can find out this one. But the very difficult part was trying to state what is being done for this natural language statement. So it is moving in a circle, and the small m and capital M is connected by the string. And then this circular motion will generate a certain force that will have bring those this capital M upward by our tension on the string. And then we have a two equilibrium. One is for the small m for circular motion and the capital M for under the gravitational force. And then by doing so, we can find out the velocity, okay? And it is a little bit similar to previous problem, but it is, you might think that it is different, but basically it is more or less similar. So now, a ball suspended from a pivot on a string over length L is given, revolves in a horizontal plane. This is the plane. With a constant speed of v. The string maintains an angle of zeta is given by this one, and with respect to the vertical, find velocity taking gravitational acceleration is this one. And then what we have to do is that eventually we need to go to this force balance. And we need to identify what kind of forces are given. So let's try to understand what is given here. So the length is given, zeta is given, g is unknown. And then let the mass move in the horizontal circle of the radius r. R is given by capital L times sine theta. Note that this is L theta. Okay, so that we have this relationship. And then once it is hanging by this string, then there is a tension here in this way. It is moving always away from the object. Okay, and then if you look at it more carefully, then if there's a tension, tension has a two component here, vertical and this inward horizontal one. So vertical case is if it is theta, then it's also theta, so that the vertical component becomes t cosine theta, and the horizontal component becomes the t sine theta. And then we have a two equilibrium, to cancel out, to balance. One is the vertical tension should canceled with the gravitational force. Otherwise, if there is a force, then it should not be on a horizontal plane. It should move up and down. So if there is no motion across this horizontal plane, that means the tension vertical component should match the gravitational, that is downward. Upward, downward force should cancel out. And then if it is want to keep it as a circular motion, this horizontal tension should match that of the central fatal force for circular motion. So we have a two equations, right? And then what we need to know is actually V. But in this case, we have these two equations, and then actually T is not known as well. So basically, two unknowns for the two equations, then you can solve it, okay? So, but anyway, what we can do is that divide the horizontal by vertical, we can find out tangent theta is given in terms of this value, okay? And then we note that R is given by this one. And then here, the relationship between the V and all the known parameters R, G, theta is given like this. So in other words, in this case, so you can find it here. So that one good thing about these two equations is that you eliminate T, okay? And then you left over only one unknown, V, okay? That's the way to bring the two equation into one equation with the one unknowns. And then V square is nothing but RG tangent theta, okay? And then R is given by this formula, and then if you just then you can find out this value, and then you can find out V numerically, okay? So once again, in this case, as we have done before in the case of this rotating object hanged by the larger mass, then we have to think about the two equilibrium conditions, right? 1 and 2. And similarly, in this case, we have to think about two equilibrium for vertical and the horizontal. Okay, and then we can find out two unknowns. And now it's time to think about more about the frictions. So we have already discussed the frictions in some of the previous problems, but we are going to focus on friction itself. Okay, so the figure shows a block with a mass M1, here M1, on a horizontal surface connected by the massless string to hook where the M2 can be increased smoothly. So here M2. The pulley has a negligible mass and no frictions when M2 is given by this one, it begins accelerate downwards at the rate of this acceleration. Note that the unit is meter per second square is its acceleration. Calculate the difference between the static and the kinetic coefficient of frictions, μs and μk, between M1 and this surface. The friction is happening. Note that no friction here, no friction here. And then only friction you can think about is this M1 and this horizontal surfaces, okay? And as you might know, there is static friction, which is μs, and then kinetic, μk. And then the μs is, as the name stands for, the frictional coefficient when M1 does not move. And then kinetic frictional coefficient is when M1 moves, there is also a frictional coefficient. And then the problem is calculate the difference between the static and the kinetic coefficient. This is what we need to find out, okay? So to summarize, M1, M2 is given, and the pulley string is ideal. That means that there is no mass, no frictions, and table is horizontal perfectly. And when M2 is this one, then it starts accelerate downward at given this A, and find out US minus μk. Okay, so now let's try to think about what is going to happen just before the motion, For M2, we have a string, then we should have a tension. And then we have another one is tension. Note that tension is always moving away from the object, okay? So for M2, we have a gravitational force, M2g, and it should match the vertical motion. So note that at the instant before any motion, acceleration is 0, and the static friction is at its maximum. And then we can have, since it is not moving, tension and the M2g, the gravitation, should cancel out. And for the M1, it doesn't move. If it is not moving at all, that means if we have a M1, there is a normal force downward, M1g. And then this is normal force downward. And then you have a static frictional coefficient, and then that becomes your static force, okay, for M1. And then kinetic phase, once it moves with the given accelerations, and then let downward for the M2 toward the pulley for M1 be positive. So that in this case, toward the heels. So M1 moving in this way is a positive, and M2 moving downward is positive. Okay. So M2G, there is a tension and M2G. And then if it is start moving with the accelerations, that means the force difference M2G minus T should be same as the acceleration times M2. So for this motion, okay. And for M1, there's a tension, and then there is a frictional force, which is moving because it is the kinetic. And then this is the T minus Fk. It is tied to the same string, such that if it is moving with the acceleration A, then this should be also moving with the acceleration A. That's the key thing. So you need to plug in A here as well as A for M2 and M1. In other words, if it is connected by the string, the two objects cannot, we are going to assume that the two objects cannot move in the separate accelerations. So one object is moving in the acceleration A, the other object should be also accelerating with the same acceleration A. So this is what it says. This is a very important thing you need to remember. This is possible because it is connected by your ideal string, okay? And then Fk is kinetic, friction is mu k times n, and here is m1g, is downward. And then we have these equations, and then we have t can be eliminated, and then we have this one, and we get mu k. And then, so we have mu k is given like this one, and we have mu s is given by this one already. Note that what we have done. So in the static threshold, just before the motion, we note that there should be no acceleration. So that T and the gravitational downward force should be matched together, as well as the tension should match with the frictional force, which is the static. Okay, these are the two requirements, and from this you get mu s. Okay, that was one thing. When it starts move, then we should realize that two objects should accelerate with the same accelerations. Okay, so that's the things we have to consider, such that the force difference is going to be given by ma. Note that F equal to ma for M2, for M1. Okay, and then from this Fk, we now know the mu k. Mu k can be found in these two equations, and then mu k is known. And then mu k minus mu s minus mu k can be evaluated numerically. And now let's try to think about more or less similar work, but we have an additional force. So M1 is given, horizontal surface is connected to M2, okay, and it is string, okay. The pulley is massless and frictionless. A force over this much act on M, this magnitude has been given at an angle of 30.9 degree. The coefficient of a kinetic friction between the M1 and the surface is given by this mu k. Determine the upward acceleration of M2. So we need to find out what is the acceleration of M2 upward. Okay, so if you look at it, force is given on M1 in this direction, so that it will bring M2 upward. So we need to find out the accelerations. So let's summarize what is given. M1 is given, force magnitude is given, with the zeta is given, mu k is given. And then we need to consider what is actually F does for this system. F can be decomposed into vertical and horizontal. Okay, so Fx, so here's the zeta. So along the x directions, we have a F cosine theta. Along the y directions, we have this one, right? And then we can have a certain numerical value. The normal force on M1 and the kinetic frictions, what is going to happen here is that all the force on M1, so note that there's M1, and of course there's a M1G gravitational force, and then there's an Fy here, and then we should think about the we need to think about what else we can think about is the normal force. So a particle balance on the M1. So M1 does not move up and down, such that we have a gravitational force and then normal force. Normal force. So let's try to think about Fy is, yeah. So what we are going to have is that we need to be careful about the sign. How do I? Okay, so I should be careful. So here is the normal force, and the Fy is in the same direction, but it is opposite to the gravitational force, so that we have a plus and minus sign here. And it should be 0, okay? Otherwise, this M1 will go up and down, okay? And to stay at the horizontal without any vertical motion, we should have this equilibrium. And then we can find out the normal force is given by this one. And then kinetic frictions, and it's given by mu k times n. Here, it is very important to note that if there is no Fy, then we know that normal force is m1g. But because of Fy existing, because we have this Fy non-zero, so that we have these equations. N is m1g minus Fy. This is the things. So what is happening here is that if there is no force, the normal force would be identical to the m1g, but because of this Fy, normal force is actually decreased. Okay. So anyhow, in this case, normal force is found, and then we can find out the kinetic frictions. And now it's time to think about what is going to happen with this object one by one. So we have a M1, M2, okay? So we have a two object, and then we have to make what forces are actually applied to these two objects. For M1, along the horizontal case, so note that tension is here, and the friction opposes the motion. such that fx minus t minus fk is m1a. So here is the important one. So here, what is happening here is the frictional force as well as, I'm sorry, we should make a good sign here, sign convention. So note that if you look at the M1, we have, let's try to think about more clearly. So initially, what we have here is that so there was a fx, right? Remember that there is the fx, right, on M1, okay, fx, right? And then here is the fx. And the friction, by definition of friction, is opposing to this force, so that we should have a fk, okay? That is the thing we need to think about. So fx is these directions, and then is opposing to the tension, and then there is this also frictions. So this sign is very important. If you do not have the right sign, then it's going to be screwed up. So anyhow, this is the old forces acting on the M1, and then it should be M1 times A. Note the Newton's law, ma. All the force is shown here, and then it should be same as m1a. And then this acceleration should also apply to the m2. So we have m2a. And then for this case, t is upward, and then gravitational force is given by this one. So it is opposite sign, so t minus m2g is m2a. So once again, if it is connected by the strings, so that once one of them is moving with the acceleration a, that means the other should move with the same accelerations. That is the very important thing. You need to have this a and this a, okay? And then from these two equations, and then we can get rid of the t. So t is given by this one, and then just plug in the t here. And fx is already given, right? And then we need to find out a. A is given by this formula, and then you just plug in all the numbers, and you can get the accelerations in terms of a meter per second square. So it's a little bit complicated, it might be, but once again, you have a two object under the different forces. You need to figure out what forces are acting on each object. And then a very important thing is that if one of them is moving, then it should be in the same accelerations. M1 and M2 should be in the same accelerations. That is a very important one. A driver in the car with the mass of this much applies the brakes when the car is moving this, and then car comes to a rest after traveling 65 meters. What is the magnitude of a net force on the car causing its deceleration of the motion? Okay, so initially it was initial velocity is given with the mass. And then let's say from here to here is 65 meters. And the final velocity is 0, comes to rest. That is the very important one. So VI is given numerically, mass is given, and the final velocity is also given. Okay, And then this is the very important step to understand what is going on. Then the car comes to rest, means is the final velocity is 0. This is the very important step. Anyway, you convert it into the meter per second. And the reason why we need to convert to this is that we need this conversion to find the force in Newton, kilogram times meter per sec square. So that's the reason why we are going to convert it into meter per second. And then we know that the velocity problem, V final scale minus V initial scale, is given by 2as final minus s. Okay. And then plug in these numbers. We know what the V final is. It is 0. And this is our initial velocity. And then we know what the s is 65 meters. And then we can find out what is the a is. And then once we find out the accelerations, that means, and we can find out the force, F is given by ma. Okay, this is what we get. Next one, a force F lifts vertically chain consisting of 5 links. It's 1, 2, 3, 4, 5. And the chain is lifted with the constant acceleration of magnitude sk given by. What is the magnitude of force that link 3 exert on link 2? The gravitational acceleration is given by this one. So what we think about is that first of all, we summarize what is given. So m is given, acceleration is given. Find the force that link 3 is exert on link 2. So the force between these two. And we need to choose a subsystem, consider the lower part of the chain, links and 1 to 2 together. Let T32 be the force link 3 exert upward on the link T. So the reason why we have to think about 1 and 2 is that the force will exert on the 2, but it is linked to the 1, so that the total mass would be not just the mass of the link 2, but it is 1 and 2, okay? So that we have a T32 is upward, and then weight m subgroup is 2m. So mass 1 plus mass 2, okay? That's the thing. And then applied Newton's second law, it should be same as this one. Tension minus this subgroup gravitational should be same as F equal ma. So that you get this relationship, and then we can find out the T32. Here, important step is that it is moving with the same accelerations. And then we are just looking at the 3, the magnitude of force that link 3 exert on 2. And then if you look at it, they are all linked such that we have to think about 1 and 2 forms a subsystem. That's the thing. A force F lifts vertically a chain consisting of 5 links. A chain is lifted with constant accelerations. Once again, same thing. Find the magnitude of force F that must be exerted on the top link to achieve these accelerations. So it's on the top. F should be calculated, but in order to get it, then you have to think that all of them are linked together so that we have 5 masses together. And then F is acting on this 5 mass against the 5 mg, which is gravitational force. F minus 5 mg should be should be accelerations. Okay, so F minus 5 mg is going to be 5 ma, so that we get this relationship. Okay, here capital M is 5m. Okay, so that we have this one. Another one, there is a banana at the top of a long rope. Okay, a monkey of a mass m starts to climb up to reach a banana. Rope will snap if the tension exceeds this value, Newton. Calculate the least amount of time monkey could take to reach the banana without breaking the rope. The gravitation is given like this. So rope length, we note that from the initial position to banana is given. So S is given. And the monkey mass is known, and gravity is this one. And rope snaps if T is over T max. So note that monkey is under the influence of two forces. One is the tension, and the other one is a gravitational force. So if the monkey accelerates upward with the acceleration a, then we have a total force T minus mg should be same as ma. And what we want to have is that this T should be less than T max, okay? Such that we have a range over A, okay? Then maximum allowable acceleration is given by uh, this maximum allowable acceleration is actually T max over M, which is given by A max is given by this one. Note that this one, okay. This is one thing we need to find out. And the maximum allowable acceleration you can think about is actually if it is have this T max is the force and divide by the M, and then we have this range. This is the A max. And then what we have to do is that time to cover the distance with the A max. And then we note that S should be same as this value for constant accelerations. And then we can get this value. Okay. And the next thing is that two loops are connected to a steel cable that supports the hanging weight, the steel cables. So we have a tension on the left-hand side and tension on the right-hand side. Note that they are not identical because they have a different angle. For the left-hand side is 60 degree, right-hand side is 40 degree, and it is matching the whole weight. So if the maximum tension can sustain without breaking is this one, determine the maximum value of a hanging weight that those ropes can safely support. So we need to find out what is actually given. So let the tension in the left and the right is TL, TL, and the hanging weight is W. And then the resolved forces at the junction, and let's say this is the Y direction is positive. And then we note that horizontal cases, these horizontal forces should cancel each other. And At the same time, these two forces, the tension, is actually adding up along the y directions. So vertical component TL sine theta is given by this W. So we have an equation 2. And then we need to find out which loops limits first. From the equation 1, we get this one. TL over TR is going to be this one. That means tension of the left-hand side is larger than right-hand side. So that means as weight increases in the second equations, then the left loop reaches its first limit because left-hand tension is larger than right-hand tensions. Those are at the safe maximum so that it reaches the given limit. And then from this relationship, we get the TR is given by this relationship. And then we get this value. And note that this is well under the limit. Okay. And then maximum supported weight can be furthermore calculated this weight. We calculated the maximum tension, left and right. And then this will give you our weight, maximum weight. Okay. And now let's try to think about another problem. A block with a mass M1 is placed on an inclined plane with the slope angle alpha is given by this one, and is connected to the second hanging block, so M1, M2, by a cord passing over a small frictionless pulley. The coefficient of kinetic friction is this value, and find the mass of M2, for which block M1 moves up the plane at a constant speed once it is set in the motion. Let up in the plane be positive for M1 and downward be positive for the hanging M2 because it is the same directions. Okay, if it is positive, and it should be also positive. Okay, so let's try to have try to analyze what forces are acting on. Because we have two objects, we have to think about what forces are actually exerted on each of the masses. For the M1, along the slope, the tension acts up the plane. And component of gravitation, M1g sine alpha, M1g sine alpha is downward. Okay, this one. Kinetic frictions, Fk is given by mu k times n. Normal force is this force, m1g cosine alpha times mu k. Now, it's actually down the plane. Note that friction is always opposes the motion. That is the key things. If it starts to moving up, then friction should be always moving downward. So this is the direction of a friction. So assuming there is no accelerations, how do I know it? Moves up the plane at constant speed. This is the clue. That means we have no accelerations. Okay, so that means no acceleration means these forces along the M1. So M1 is given by M1 G sine alpha downward, tension upward. This is frictional force downward. And then if you add them all together, it should be 0 because F equal to MA and A is 0. So what we know is the t is given by this value, okay? But we are not yet done because we have another object, M2, okay? For the M2, with the same acceleration, note that we are keeping the rule. Once it is moving in the acceleration, and then those two objects should be moving with the same acceleration. So here acceleration is given as a 0, so that M2 should be 0 acceleration. That means uh, the net force working on the M2G minus T is 0. Okay, is M times A is 0. So we have a M2G. Then we have a previous case, we have a T here, we have another T here, and it should be equal. So that we have these two equations. And then finally, we can find out M2, okay? And then we can calculate it. And now, nearly same situation, but we have different conditions. So M1 is given, alpha is given, M2, and then the coefficient of kinetic friction is given, and find the mass M2 for which block M1 moves down the plane at a constant speed. Note that previous case it was moving upward, but now it is moving downward. So it's the opposite case. Then what is changing? The condition is more or less the same. And then once again, at a constant speed means is that the acceleration is 0, okay, for both M1 and M2. And then let's look at the force along the incline on the M1. Then we have this gravitational that is moving downward, and then there is a tension moving upward. But in this case, importantly, the friction, kinetic friction, is actually up because this M1 tries to move downward. Then friction is always opposing to the motion. So we have a different sign, right? M1G minus T minus this one. So that if it is the plus direction, then both friction and tension is minus. That's the big difference. And then from this, you get the tension. And then for mass 2, we are applying the no accelerations. T minus M2G was M2 times A, which is 0, so that we have 0, so that we get this one. So we have a two equation for the T, and they should be equal. And then we get M2. So the statement, natural language, M1 moves down the plane at a constant speed. M1 moves up the plane at a constant speed. It gives you very different physical equations. Okay, so that's the thing you need to take note. And now let's try to think about another problem. Block A weighs this, and then this one. So note that the weight is given. Actually, this is M1G, and this is M2G. So that's etc. And coefficient of kinetic friction between all surfaces is given like this. Find the magnitude of the horizontal force F necessary to direct a block B to the left at a constant speed. So no accelerations. If A rests on B and moves with it. So that this is the statement, natural statement, how we are going to translate into our physical model languages. So choose a system, treat A plus B together as one body at constant speed means that there is no accelerations. Okay. And in order to find out what is happening here, and then the external horizontal forces on the system is given by the force and the kinetic friction at the floor opposing the motion, frictional force. Since A does not slip on B, there is no kinetic friction at the A minus B interface. Okay, such that we have we don't have to consider frictional force between the A and B. The only thing we have to think about is this frictions. Okay, and then normal force on the floor is with these two weights A and B rolled together. And then we have normal force is given by this one, and thus the flow friction is given by this one. And then the force balance should be such that total force is given by Fk. So frictional force is always opposing the motion. It should be M A plus B A, and A is 0, such that so F should be Fk, so that we can find out the value. Now, it looks very similar, but it's a little bit different. So note that A is tied to a wall. So coefficient of a kinetic friction between all surfaces, that means here, here, okay? Find the magnitude of a horizontal force F necessary to direct B to the left at the constant speed, once again. For B, acceleration is 0. But there is a condition. If A is held at rest, A is held at rest. So, we need to think about what is happening here. So note that in previous case, A and B moved as one body, And even though there is a frictional coefficients given, we did not consider any friction force between the A and B. Okay, this is the important statement. But in this case, A is at rest and B is pulled back. Okay, so we need to think about the two cases between B and floor. So here, and then between A and B. So this is the big difference. So that normal force on the floor is given by 2 weight, and that is given by this one. Between A and B is actually A is working on this, so that only the WA is be the normal force for A and B. Okay. And then kinetic friction opposing the motion of B. Then we have two things: floor friction on B, so that F floor is given by mu k times N floor, and the friction at AB interface is given by this one. Okay, and then total resisting force on B is given by floor friction and then AB interface friction. Add them together. Okay. And then in order to balance for constant speed, that means A equal to 0, then note that we have a F is this directions and the fraction is this direction, such that f minus f total is mb a, and then this becomes 0, such that the 0, so that we have this relationship, and then you can find out the force. And small remote control car, RC car with a mass 2 kilogram moves at a constant speed in a vertical circle inside a hollow metal cylinder that has a radius of 4 meters. What is the magnitude of a normal force exerted on the car by the walls of the cylinder at point A, the bottom? So we have to think about the forces, all the forces on this car at the position A. Then in order to find out what are the given, the mass is given, speed is given, radius given, and the gravitation is given. At the point A, the central force acceleration at the bottom is actually, so if you just, is upward. So it is given by this acceleration, centripetal force. And then there is a normal force, and from the wall is upward, actually. Note that it is moving in these directions, so that the normal force in this A position is actually upward. Okay, normal force is upward as well. So that while the weight mg is downward, so that n minus mg should be equal to this centripetal force, and then n is given by this one. Okay. And it's time to think about the other case. So what is the normal force acting on A, and what is the normal force acting on B? The main difference here is that the sign. So normal force here is opposed to the gravitational force. But note that normal force is actually if you have a certain body, and then it is in this direction. It's a surface to the body, surface to the body. So surface to body is, in this case, is normal force here. But in this case, surface to body is upward, okay? This is the very big difference. So in this case, normal force is downward, so that we have a same sign as the gravitational force. And then in this case, this should be matched with the centripetal force. And then from this, we can find out the normal force as well, okay? So very important distinction between these two cases is that the direction of normal force. Normal force is always, if you have anything on the surface, surface to object. Okay, that's the normal force directions. Okay, that's it. I hope you could learn from these sessions so that you could be well prepared for your exam 1. Good luck.